Swayam Prabha. Digital India. Educated India.
The next presenter is C. Cheng from University of Manchester. This is also presentation in virtual mode. So I request C. Cheng to make a presentation, actually share his presentation, and maybe in 1 minute we can start. Mr. Cheng, can you hear us?
Yeah, hello. Please wait for my video.
Thank you.
Hello everyone. I'm Xi Cheng. I come from the University of Manchester, and today my topic is multi-scale simulation of morph-based membrane separation for CO2 capture via the integration of molecular simulation, artificial intelligence, and process modeling. The following presentation will be divided into 6 parts. Here is the introduction, methodology, molecular simulation results, machine learning prediction results, membrane separation process simulation results, and the conclusion part. The following presentation is divided into 6 parts. And the following, let me introduce the introduction of the research design framework. Based on the fact that the process of membrane separation is generally permeation, we apply the classical solution diffusion model to calculate the solubility and the diffusion coefficients of gas molecules on the different operating conditions. And we're using the molecular simulation to simulate the from the molecular level and generating a large amount of molecular simulation data. This big data set is also integrated into the process simulation of all the fiber membrane process by the machine learning techniques such as the artificial neural network. The membrane separation model is based on the tanks in series model, and the system of the partial differential equations is solved by the finite volume method. In this way, multi-scale computer-aided integration simulation from the molecular level to the process level could be achieved. And next, we move on the research background. When talking about the research background, people are most concerned about why CO2 capture and gas separation are necessary. With the rapid development of economy and the increasing demand of energy consumption due to the large-scale industrial application, more and more greenhouse gases such as CO2 and CH4 are being produced and released, which leads to the serious greenhouse effects such as global warming. So the most important is the extraction of the natural gas fields and many other methane resources is also increasing with the separation of its primary components, CO2 and CH4 is becoming particularly crucial. So before it could be used as the liquefied natural gas. For this industrial application, CO2 and CH4 gas mixture separation, the molar composition of CO2 in the feed gas is widely distributed, covering a wide range from 30% to 90%. So it makes it urgent to develop the new technologies such as the membrane separation for the efficient separation of CO2 and CH4. So if you want to remove the CO2, there are different processes could be used, such as the distillation, the PSA, and absorbing, absorbing. So how about the advantage of membrane separation process? So firstly, it is different from the traditional amine absorption. Membrane separation is a physical change and has no requirement of the chemical reagent. So it is easy to operate, control, and scale up into the industrial application. Due to the membrane separation uses selectivity, functional selectivity, so it has high separation efficiency and no energy consumption. And membrane separation efficiency is mainly characterized by 2 parameters. One is the permeability and one is selectivity. The permeability reflects the flux and the selectivity reflects the purity of the product. So high selectivity can achieve the high purity, which reduce the rely on other complex unites such as distillation. So the high permeability means a smaller membrane area to achieve the same flux, which reduces the capital cost. According to different materials, I think the membrane could be separated into the polymer membrane and the porous materials membrane. For traditional polymer membrane, it has the trade-off between the permeability and the selectivity, but for the porous material membrane, it has the absorption and the pore saving effect, so it can break through the limitation of the trade-off. After the research background about the CO2 removal from the raw natural gas and the many ways we can do it. So I'm going to concentrate on the membranes and how to improve the membrane separation technology. So previous studies have focused on the relationship between the pore structure and the properties of MOFs, or just screen the MOFs in the existing database to find them with the application potential. All these studies only report the properties of MOFs at room temperature and a fixed pressure. However, we pay attention to the influence on the operating conditions on the performance of membrane process, which cannot be ignored for the economy and energy consumption. So in this work, IR-MOF1 is one of the stable, synthetic, and industrialized MOFs, and it has been successfully applied into membranes. So it also the parent of the classic IR-MOF series. So it has a large number of available and comparable experiment data, so as to be selected as the research material in this work. However, I think the method of this work is not limited to IR-MOF1, but can be extended to any other MOFs. So let's move on to the details methodology. So first is the molecular simulation method. The molecular structure of IR-MOF1, including the central metal cluster and the organic ligand. And Monte Carlo is a random sampling method, which only involves the information about the system configuration. The energy of the system is described by the force field function, which is a potential energy function describing the non-bonding and the describing the bonding and the non-bonding interactions. So GCMC method adopts the MUVT ensemble, which is often used to simulate the absorption capacity and the heat of the heat of absorption the heat of the absorption gas molecules inside the porous materials. So through the randomly insertion, movement, rotation, and the deletion of the gas molecules, the final system could tend to achieve the equilibrium. So the generation of the microstate in the molecular dynamics depends on the classical Newton mechanics. The path of molecules motion is obtained from the Newton equation, the classical Newton equation. Through this statistical analysis of the molecular coordinates, velocities, and forces, we can obtain the kinetic properties such as the diffusion coefficient. And the details simulation parameters can find here. The binary gas mixture with different ratios can be used as the feed natural gas, landfill gas, biogas, and shale gas. And 6 temperatures with pressures between 0 to 20 bar, as well as the feed CO2 fraction from 10% to 90%, are selected as the membrane separation process condition. So the solution diffusion transport model is also used to calculate the permeability. And here is the 7 criteria used to evaluate the absorption-based storage performance and the permeation-based separation performance. Here we utilize the artificial neural network as the machine learning technique. Dataset consisting of 1340 points is used to randomly select data, of which 70% is used to training, 15% is for validation, and the last 15% is for the test. Is used to test the model. The early stopping method is performed to avoid the overfitting problem. here, the input layer contains 3 features and the output layer contains 2 features. The performance function in the artificial neural network is the mean squared error, and another criteria is a square. And a text in series model is applied to represent the dynamic performance of the hollow fiber membrane under a wide range of operating conditions. Here, the figure presents a schematic of the text in series model for the hollow fiber membrane. The feed is introduced from the shear side, and the permit is gathering from the inside of the fibers. The model includes the relationship governing transport across the membrane, the mass balance equations, the pressure drop equation, and the boundary and initial conditions. This mathematical model is simulated using the finite volume method, and the membrane area, the product purity, and the recovery are used to assess the process performance. So let's move on to the results part. The first one is molecular simulation results. This page shows the absorption items of pure CO2 and stage 4 at different temperatures. The fitting degree of the Langmuir extended model is greater than 0.99. It is worth noting that with the increase of the pressure, the absorption item of pure CO2 presents the S-shaped step, which is completely consistent with the phenomenon observed in the experiment. So meanwhile, the storage capacity of CO2 is much larger than that of stage 4, the pure stage 4. And the next page shows the absorption items of the binary mixture. It can be seen that the absorption capacity of stage 4 decreases significantly, while the absorption capacity of CO2 is only slightly lower than that of pure CO2. And from this page, you can see that the CO2 is more easily absorbed than stage 4 and still shows the obvious S-shaped step. So this is because there is a competitive relationship between the absorption of the binary mixture, and the CO2 obviously plays the dominant role in the competitive relationship. Because stage 4 occupies a small amount of CO2 absorption sites, so it results in a slight decrease in the CO2 capacity in binary mixture. And the next is the diffusivity and activation energy of pure gas. At the same pressure, the activation energy of CO2 is greater than that of stage 4 because stage 4 is lighter than CO2 and it can diffuse easier to diffuse. The activation energy of stage 4 decreases with the increasing of pressure, and conversely, the activation energy of CO2 increases with the increasing pressure. This slide is the diffusivity and activation energy of the binary gas mixture. So it can be seen that the activation energy of CO2 in binary mixture is always less than stage 4, which is completely contrary to the conclusion of the pure gas in the before slides. So this is the result of the competitive absorption and the synergistic diffusion simultaneously in the membrane separation of the binary mixture. A large amount of preferentially absorbed CO2 enter the pores first and block the pores, making the diffusion of stage 4 in the membrane extremely difficult, and the activation energy of stage 4 increased significantly. The synergistic diffusion effect also makes CO2 easier to diffuse than the pure state, and its activation energy decreases accordingly. To evaluate the effect of different temperatures and pressures on membrane separation efficiency, this slide shows the functional relationship between the permeability and selectivity, as well as the traditional polymers Robinson upper bound. It can be seen that the selectivity of IR-1 increases with the increase of permeability, which is different from the trade-off between the polymer membrane. At some temperature and pressure, IR-1 membrane can break through the Robinson trade-off with the high permeability and the high selectivity simultaneously. So higher permeability and selectivity results in the higher flux, and higher purity, which means less membrane area is required, making the equipment cost less. At the same time, however, the high permeability and selectivity require the higher pressures and the lower temperatures, so which are more costly to operate. And next, move on to the machine learning prediction results part. Since different temperatures and pressures lead to greater difference in membrane permeability and selectivity, so it has important impact on the purity, efficiency, energy consumption, and cost. So therefore, it is necessary to establish a prediction model based on the results of molecular simulation by the machine learning method, such as the artificial neural network. So here is the figure reviews the parity plot of the suction capacity and self-diffusivity based on the operating condition features. The statistical metrics of MSE and R-square provide the evidence that the AL model trained on the basis of GCMC and MD simulation datasets can accurately predict the absorption and the diffusion of CO2 CH4 binary mixture in IM of one membrane. And this is membrane separation process results. The developed AL model are integrated into the oral fiber membrane model for dynamic simulation of the separation of binary mixture. We consider three different sources of CO2 and CH4 binary mixture, such as natural gas, landfill gas, and shale gas. They hold a different fraction of CO2 in the feed gas sources. So in step one, it plans to upgrade CH4 purity from 30% to 65%. Continued with step two, it plans to upgrade the CH4 purity from 35% to 80%. Lastly, it plans to upgrade the CH4 purity from 80% to 90%. Then, in order to further increase the purity of CH4 from 90% to a higher percentage to meet the requirements of liquefied natural gas transportation, it should be carried out by pressure swing absorption technology, such as means PSA. So here is the form of the geometric and parameters and operating conditions for process simulation. The simulation results for three case studies are shown in this figure, including the flow rates, the mole fraction, the pressure, the partial pressure difference across the membrane, and the permeance in each tank. So it can, as can be seen in each tank, the permeance of IM of one membrane is greatly dependent on the partial pressure difference across the membrane. So as a result, there is a non-negligible difference in the transport of the gas across the membrane. So three case studies by process simulation of the separation of CO2 CH4 gas mixture from three different resources indicates that the IM of one membrane is able to produce the greater recovery with significantly smaller membrane area than traditional polymer PTMSP membrane. So it can get the results from the before introduction. So in summary, the integrated design framework we initially produced is well demonstrated, and with the example of IM of one, it provides an integrated idea for future optimization, process condition, and the design of optimal membrane material. So in the future, it stands to perform optimization to find the optimal operating conditions. And we should conduct a comparative economic and energy consumption study of MOF membrane process with other conventional processes such as PSA. Here is all for my presentations. Thank you for the questions.
Yeah, thank you for your presentation. We have like 2 minutes to ask any questions.
Yeah.
I will ask first the audience here. Anybody in the audience has a question?